Section 24.4. Obtaining the value of the electric field. In this session, we will explore how to derive the electric field from the electric potential. We begin with an outline of our key topics, starting with the fundamental mathematical relationship between the electric field vector, E, and the potential, V. We will define the electric field as a gradient of the potential and examine the specific geometric relationship between equipotential surfaces and electric field lines. Noting their orthogonality, our discussion will extend to calculating field components using both Cartesian and spherical coordinates. Finally, we will introduce the method for finding the electric potential created by continuous charge distributions, moving beyond simple point charges to more complex systems. To understand the relationship between the field and potential, we look at the potential difference, dV, between 2 points separated by an infinitesimal displacement vector, d. S is defined as the negative dot product of the electric field and the displacement. If we simplify the scenario to a case where the electric field only has an x component, the dot product reduces to the magnitude of that component times the change in x. This leads us to a fundamental calculus-based relation. The x component of the electric field is equal to the negative derivative of the electric potential with respect to x. Essentially, this tells us that the electric field represents the spatial rate of change of the potential. The negative sign is crucial, as it indicates that the electric field points in the direction of decreasing electric potential. This mathematical relationship has significant practical applications for experimental physics. Because we can easily measure electric potential using a voltmeter and track position with a meter stick, we can determine the electric field empirically by measuring the potential, V, at various positions along a line and plotting those values on a graph of V versus X. We can analyze the resulting curve. According to our derivative formula, the slope of the graph at any specific point gives us the magnitude of the electric field at that location. While we often focus on the x-axis for simplicity, the same logic and experimental methodology apply to the y and z components of the field, allowing for a full three-dimensional reconstruction of the electric field from potential measurements. A vital concept in electrostatics is the equipotential surface, which is any surface consisting of a continuous distribution of points having the same electric potential. Along such a surface, the potential, V, is constant, which means the change in potential, dV, is zero. When we look back at our dot product formula, if dV is zero, then the dot product of the electric field and the displacement along that surface must also be zero. This leads to a key geometric conclusion. The electric field must be perpendicular to the displacement along the surface. Therefore, electric field lines are always perpendicular, or orthogonal, to equipotential surfaces at every point in space. This rule helps us visualize the field by looking at the potential, and vice versa. We can visualize these relationships through different charge configurations. In the first image, labeled A, we see a uniform electric field produced by an infinite sheet of charge. Here, the field lines are parallel, and the equipotential surfaces are a family of planes perpendicular to those lines. In image B, we see a point charge, which creates a spherically symmetric electric field. For this setup, the equipotential surfaces form concentric spheres centered on the charge. Finally, image C illustrates an electric dipole. You can see how the dashed blue lines, representing the equipotential surfaces, twist and curve to maintain that perpendicular relationship with the orange electric field lines. In every case, whether the field is uniform or complex, the 90-degree intersection remains a constant rule of physics. To handle different geometries, we generalize our mathematical approach. For a spherically symmetric charge distribution, where the potential, V, depends only on the radial distance r, The radial component of the electric field is the negative derivative of V with respect to r. In a more general three-dimensional Cartesian system where V is a function of x, y, and z, we use partial derivatives to find each component. The x component is the negative partial derivative of V with respect to x, and similarly for the y and z components. We can wrap this all up into a single vector expression using the gradient operator, represented by the del symbol. This notation compactly shows that the electric field vector is the negative gradient of the electric potential. Let us check our understanding with a quick quiz. First, consider a region of space where the electric potential is zero everywhere along the x-axis. Since the potential is constant at zero, its derivative with respect to x is also zero, meaning the x component of the electric field must be zero. Now suppose the potential is a constant positive 2 volts everywhere along that same axis. Even though the absolute value of the potential has changed, it is still constant. Therefore, the derivative is still zero, and the electric field component remains zero. The important takeaway here is that the electric field does not depend on the absolute value of the potential at a point, but rather on how that potential changes over space. When dealing with continuous charge distributions rather than discrete point charges, we use integration. To find the total potential at a specific point P, we divide the entire charge distribution into tiny elements of charge, denoted as dq. We treat each element as if it were a point charge located at a distance r from our observation point. The graphic shows several of these elements, like dq1 and dq2, contributing to the potential at point P. By integrating the contribution of each element, which is the Coulomb constant K times dq, divided by ρ over the entire volume or surface of the distribution, we arrive at the total electric potential, V. To summarize the key points of this section, remember that the electric field is the negative gradient of the electric potential. In one dimension, this is expressed as the negative derivative of potential with respect to position. We have established that equipotential surfaces and electric field lines are always perpendicular to each other. For systems with spherical symmetry, the radial field is found by taking the negative radial derivative of the potential. In 3 dimensions, we utilize the gradient operator to relate the field vector to the scalar potential function. Finally, for continuous charge distributions, we calculate the total potential by integrating the individual contributions of infinitesimal charge elements across the distribution. To wrap up, consider these review questions to test your grasp of the material. First, think about why the electric field must be zero in any region where the electric potential is constant. Try to justify this using the mathematical derivative relationship we discussed. Second, if you are told that the equipotential surfaces in a specific region are a series of parallel planes, what does that imply about the direction and the uniformity of the electric field in that area? Reflecting on the perpendicular nature of field lines and the definition of a gradient will help you answer these questions.